So I can tell you that I gave this talk a few weeks ago in Brazil. So Chaba heard it, that's why he really wants me to end early. But the night before when I was preparing this talk, I was depressed because we couldn't finish our paper, we didn't have results. So I went to someone much more knowledgeable than I am, and the internet, and I asked Dali, which I don't know if you know, how to find dark matter using astrophysics, and this is what I got. And I'm pretty sure I'm still confused with what it's trying to tell me, but I like the title. It's very much like my English. It works out. And then last night, after the soccer game, I decided to ask it again. I don't know if you know Dali. No. So it's an awesome AI, but it's open AI app that can, it studies lots and lots of paintings in the internet, and you just give it a sentence and it paints. You can tell it to paint in any style and anything you want. So I thought it has all the information, everything is on the internet. So I thought I'd ask also, where to find, where is dark matter in Brazil, in Madrid, is there dark matter in Madrid? So maybe you guys know what this means, but for the next workshop, make sure it's over there. Yeah, and this was a logo I asked a long time ago. It's a logo for dark matter experiments in underground facility in Japanese style. And I have no idea if this means anything. Anyway, all right. So you don't need motivations. We'll be looking for dark sectors, and we want to probe them. And there are various ways of doing that. And today I want to discuss in the next 45 minutes. 43. Okay, if you need to go for the other pocket. 20 bucks is not enough. All right. Yeah, so I'll be talking about 21 centimeters. Probably that will take most of the time. Then I'll talk about the paper that came out not so long ago about probing dark matter inside stars, asking the question how much dark matter can be inside stars. So this would be looking for dark matter even if we don't interact with it directly. And if I will not have time, but I might just mention general dark mediation, how we can generally describe the interaction with dark matter and what it means, and environmental dark matter. So we'll never get there. But anyway. All right. So 21 centimeters. This is based on these two papers quite a while ago, and work in progress with Diego and my ex-student David Mazgin and Omer Katz, my current student, who's been doing an amazing work. So let me quickly review. I think many of you already know what 21 centimeter cosmology is, but I'll remind you. So the early time, dark ages, and the cosmic dawn, there's very little light. There's nothing in our universe, even though it's transparent. And so the only light we can see is 21 centimeters from this spin fleet of the hyperfine transition. And this tells us a lot about, studying 21 centimeters can tell us a lot about the reionization period of our universe. So the idea is the following: we define with these two states, and we define the ratio of the number density to be related to some effective temperature, which is the spin temperature. And the evolution of the spin temperature tells us about the early universe, those times that I mentioned. And there are basically three things that can happen. All right, so hydrogen can collide with itself or with the electrons, and so there's some rate that depends on the temperature of the gas. There are the CMB, of course, so CMB can be absorbed and spontaneously be emitted, and so there are rates that depend on the temperature of the CMB. And then there's the Lyman alpha. Once stars start to form, Lyman alpha radiation shows up and can heat up the gas through an effect which is called the Woodhausen field effect. I'll talk about it in a bit, but that depends on some effective temperature that we call the color temperature. And so the basic evolution looks something like this: the basic naive evolution for particle physicists, and I'll talk about it a lot later. So the basic evolution looks like something like this. This is the spin temperature. This is the CMB, the blue is CMB, and this is the gas, the hydrogen gas. And you see, it's up, yeah, I said that. And to understand why the spin temperature does that, we need to look at at what drives it, so these interactions. So we just write down the Boltzmann equation and you solve it, and this is the result. And you see that the spin temperature depends on the relative rates of that can happen during those early times. So first, the collisions dominate, and when the collisions dominate, the spin temperature just couples to the gas. When once induced and the emissions and absorptions become the dominant contribution, then the spin temperature couples to the CMB. And at later times, once Lyman alpha dominates, then this dominates, and then the spin temperature is just the Lyman alpha temperature. So the spin couples again to the baryons, and this is the 2000 field effect that I'll discuss in a second. So that's the basic picture for 21 centimeter cosmology. Oh, and at very early times, we have compound scattering that couple all these baths together. So that happens at very early times. Okay. Yeah, so what we measure are this so-called brightness temperature, which is the difference between the spin temperature and the CMB temperature. And what I want to be asked to ask is whether 21 centimeter cosmology is sensitive to new physics. Okay, so what do we need to kind of deform in order to see a signal in 21 centimeter that can inform us about new physics? That's the kind of the exercise that we'll be doing, we'll care about. So you could try and deform the CMB temperature, the spectrum, and this has been done. And you could try and change the spin temperature by, for instance, cooling the gas. Okay, so you remember that at some point the spin temperature couples to the gas, and if you cool the gas, then you also change the spin temperature. Cool or heat up the gas. You change the spin temperature. You can directly interact with the spin temperature, and maybe you can change the optical depth. But I'm not aware of anything that does that without very strong constraints. But in principle, you can play with any of these parameters and try to change it through new physics and ask whether you can probe or constrain new ideas this way. So that's the exercise. What can we do with 21 centimeter cosmology? So what I'm going to be focusing on is dark cooling. Simply because it looks like the most promising direction to probe 21 centimeter, to influence 21 centimeter. And the idea behind dark cooling is, again, dark matter is a very cold gas, and so if it can interact with the baryons, it will cool the baryons down, spin couples to the baryons, and therefore you would influence 21 centimeter spectrum. Now, to understand what the temperature, what gas behaves like, you again write down some Boltzmann equation, and it's very simple. There's the usual redshift, there's compton scattering, and now you can introduce whatever you want, some interaction between the dark matter and the gas. And those interactions typically have two components, essentially. One is you transfer energy from the baryons to the gas, to the dark matter, so you cool the gas. And on the other hand, because there's bulk velocity between these two components, these two fluids, once you start interacting, this bulk velocity dissipates, and so that acts to heat up the gas. So you have a heating component. So there's some competition between these two terms, and but it's very easy to draw conclusions just by looking at this equation. And the two basic implications are the following. First, in order for new physics to influence and cool the gas, you need this to compete with Compton. That just tells you that you need strong interactions, relatively strong interactions between the dark matter and the gas. And the second thing is that if you really want to cool and not heat up the gas, you need to have a good refrigerator, you need a very strong, very large heat capacity, and heat capacity is proportional to the number density of the dark matter, which means that you really want dark matter that is relatively light, because if it's too heavy, you cannot heat a lot, so you don't leave a large imprint. So we're looking for large cross sections and light dark matter. These are the two conclusions. That's where 21 centimeters can shine. Okay, so the simplest way of doing it, maybe the only way of doing it without by evading constraints, is by looking at Rutherford light scattering, because the cosmic dawn is the coldest time in our universe, and so if you can you can enhance the cross sections back then while evading constraints today. So that's the idea of why Rutherford light scattering can have the biggest effect without being influenced by constraints from terrestrial constraints and so on. And so you need a long-range force, so you need a mediator, and that mediator can be screened or unscreened. And without going into the details, an unscreened mediator is just completely excluded, long-range forces. There are many constraints. So the only possibility, essentially, is having interactions between the dark matter and the visible sector through some photon of some kind that is screened. So you could look for a hidden photon and a milli-charge, and this is the bottom line from that paper quite some time ago. And of course, as you know, what we were trying to do there is explain an anomaly, the edges anomaly. So I'll get to that in a bit. So this line here shows the what we thought, and that's wrong, what we thought would be the right cross-section in order to explain edges. But it is extremely optimistic, not taking into account any astrophysics, which I'll discuss in a moment. Okay? And nonetheless, you see that most of this parameter space is just closed by many different experiments and constraints. And there's a small window here. This regime is only relevant for spin half dark matter. So if it's a scalar, you have an open regime here. And it's interesting from the point of view that we're talking about MEV to GeV mass range and strongly interacting dark matter that is still not excluded. Direct detection cannot probe it very easily, simply because, so these are the direct detection, this is Sensei and this is Xenon, and direct detection can't reach that point simply because it's strongly interacting, doesn't penetrate the atmosphere or else. So there's an open regime, which is intriguing on its own, but a very small one. So our conclusion was this is extremely unlikely to explain the edge result, which was extremely unlikely to be correct anyway. So it worked out. Sorry. Anyways, so can we? So milli-charge was almost gone. Can you do better? And that was the goal of our second paper. And you can actually do better by understanding that influencing 21 centimeter, you needed a large fridge, and the reason you could cool the baryons was first because you can't have a strongly interacting particle that with a very large fraction, because it couples to the CMB. So you need to be below the noise of the CMB, and so you needed a low fraction of this milli-charged dark matter. And so if you have a low fraction, again, it's a bad refrigerator. The heat capacity is too small because the number density is small, and therefore you don't leave any imprint. So the way to overcome it, no longer new. The way to overcome it is to have to remember that we also have the regular CDM. If this is a small component, we have the regular CDM, and now imagine that you have some interaction between the milli-charged dark matter and the regular cold dark matter. And what you want to cook up is a simple scenario where at early times, this bath is in thermal equilibrium with the baryons, so it's under the noise, under the CMB noise. And at late times, it couples to the whole CDM, and then you have a big bath that can cool the baryon down. You're not relying on this small fraction. So you can have a tiny fraction of milli-charged particles and still influence 21 centimeters quite a bit. So, and the idea is very, very simple. implementing this idea is very, very simple. You have Rutherford interaction, of course, with the mealy charged dark matter through photons, but you also have some Rutherford-like interaction between, it doesn't have to be Rutherford, but this is the simplest realization, between these two baths. Now, between these two baths. And now remember that mealy charged dark matter can only interact with the baryons through the ionized fraction, because the hydrogen, once it's not ionized, is neutral. So in order for this interaction, strongly depends on the abundance of ionized electron fraction. And so at early times, if you look at the number of ionized electrons over the total, at early times, it's very large. There are lots of ionized electrons, and therefore this is stronger, okay? And you are in this regime. And at late times, once a recombination occurs, the fraction of ionized electrons drops, and therefore this interaction becomes small, and you are in this regime. It's very, very easy to implement. Okay? And what it does for you, was it clear? So what it does for you, if not, then ask.
I understand why it gives it like the first and the second step, but why is it like not coupled and then coupled to the CDM?
Well, I mean, there's some transition time where this rate and this rate is roughly the same, but at early times this rate just dominates, and at late times this rate dominates. So you're moving from here to here. And this transition time is not important, but it has to happen.
So at first it's not in equilibrium with the CDM, and at the end it is in equilibrium with the CDM?
Yes, exactly. Yes. Okay. So this opens up. So now we have two components. We had two components also with the mealy charged, the one fluid, but once we couple the mealy charged and CDM, we have these three fluid dynamics, and this opens up the parameter space for the mealy charged particle quite a bit. So now you see it can be much heavier, and the reason it can be much heavier because the fractions can be small. The refrigerator is still very efficient because in the end we're cooling using the full dark matter component and not just the mealy charge. And there's a whole window that can be probed here. Again, very strongly coupled dark matter. And the question is, can we constrain this with 21 centimeters? Yes.
Does this change anything in the galactic dynamics? Like this other?
Right. So we've only been studying for 4 years now,
I see.
And one day the paper will be done. But yeah, absolutely. Understanding how mealy charged particles propagate through our galaxy.
I don't mean just the mealy charge. I mean the fact that you have strong interactions of the cold dark matter with itself. With this mealy charge.
Oh, sure. Yes. Yeah. But it's relatively small, and remember, this is a tiny fraction. So really, what you mean is integrating now the mealy charged particles and looking at self interactions.
Yes.
These self interactions would be very likely to be extremely low. So to have self interactions that actually affect structure formation, you need roughly QCD like, or even stronger. You need light mediator, right? You need 1 centimeter squared per gram to have an effect on
cold dark matter doesn't thermalize.
No.
It doesn't get like isothermic.
Don't think so.
No.
Just the abundance.
I thought you were more worried about self interactions of CDM with CDM. Yeah. So I don't think it does anything. It's just the fractions are very small, and the induced, because it's relatively heavy, the induced coupling is not very large. Self-interacting coupling. So I don't think it does anything there. It would be nice, but I don't think it does anything there.
And this mealy charge in itself, does it get like what's the mass is lower than the?
No, it can be heavier. It's anywhere between 10 MeV because of the fucking BBM. Always good there. And then it can go all the way to TeV. Basically, because it doesn't matter what's the mass of this particle, the whole CDM bar is what's cooling the baryons. So all of this is open.
Can they get maybe boosted by the dark matter? Do they in the galaxy?
Well, I mean, it's boosted. So it's mealy charged. It's boosted by LGN by.
But also, I mean, they do interact with Rutherford, right? So it's like the cold dark matter itself is it's merely charged also on the cold dark matter, no?
Yeah.
So then it can it get boosted? Like if you have dark matter which is heavy, can it boost?
No. Dark matter needs to be very light in this game.
The dark matter itself, yeah, I'm sorry, I should have said it. We need the refrigerator, so we need a large number density for the dark matter, so we need a sub GV for the CDM. It's the next, right? It's here.
Oh, I see.
This is why, yeah, sorry. So,
And what's their mass ratio? Is it always big?
well, no, it doesn't matter. It doesn't matter. You know, the refrigerator is CDM, dictated by CDM, so you need that to be sub GV, same way that I mentioned it very early on. And what's the mass of the milli-charge? That doesn't really matter. It
No,
can
so
be
it
anywhere
can still
between.
be a ratio between them.
The ratio is 1 to 10 to the 6, I think, roughly.
Oh, so
Anyway,
it's
between one.
always bigger than one.
I think so, yeah.
I see.
The milli-charge is heavier, yeah.
Miniature.
Yeah. But integrating now the milli-charge, you do get interaction between CDM and electrons, which are irreducible, and so you could probe that with direct detection.
I mean,
Not the milli-charge itself.
but I mean, he's right that if the milli-charge becomes heavier, you pay a price if you want to have efficient cooling, and typically, as you see from this plot, this cross-section are excluded by direct detection.
Yeah.
Unless
Yeah.
you can model build it away, but it's ugly.
I see.
Well, it's this long.
Yeah, it's ugly.
Yeah. Anyways, yeah. What I do want to mention is that this is taken very seriously. I mean, I'm involved with some proposal to send a satellite with skipper CCDs, with the sensei detectors, to probe this mini-charged dark matter. So we're taking it seriously to try and close this window. And so if you can close it first with 21 centimeters, that's important. Okay? So there might be, okay, my experimental colleagues don't care, but I care to know whether these models are actually exist or not. Strongly interacting dark matter, does it exist or not? Yeah.
If I understand correctly, the cooling appliance by dark matter is efficient only when the two rates are both efficient at the same time.
I mean, you always have the Rutherford-like interaction, which is strong enough to cool the baryons. How do you treat it thermodynamically? Which baths are in thermal equilibrium? That's what I showed before. But you always have these Rutherford-like interactions which cool the baryons. That's, of course, otherwise you won't be cooling them. I'm going to show you the cross sections, and I mean, well, it's really here, right? The cross sections are dictated by this Q. I don't have the plot with the cross section.
But heat flow from baryons to cold dark matter is only efficient when both rates.
From cold, yeah, from baryon, yeah. So at late times, it's here. At late times, this is the picture, and you still have Rutherford-like interactions. The only thing you needed here was to evade CDM and still have a big enough bath to cool the baryons. That's the trick. The only thing that you'll be doing here. And what it leaves is a big window of opportunities
So
to.
heat flow from baryons to dark matter is always active.
Yeah, it's always active, but at early times you want the milli-charge. You know, it's a fluid that you want to couple to the baryons to flow together, so that you evade the CDM. You're under the noise of the CMB measurement, right? Distortion. Okay, so how do we constrain these models? So edges, you all know, this was a measurement 4 years ago, and they measured this huge dip where standard model was predicted to be somewhere here, and so this was claimed to be a huge, almost 4 sigma measurement of new physics. That was the initial motivation, and of course, if you look at what they actually do, you understand it's all bullshit, because this is the measurement. So what the temperature they measure 4 orders of magnitude above the noise, and there's a huge foreground which you need to subtract. Okay, and what they did was to assume so they modeled the foreground, and then they added, and without just the foreground, without any signal, they found a rather large noise that remained. They couldn't fit the foreground, and so they added this shape. Okay, some signal. That's what they call the signal. And when they did both of them together, they found that this is that the RMS of the noise is small. And so they declare that this must be the signal that they're measuring, and that's what we saw before. But that makes what very soon after it was shown to not make too much sense. And the reason is that if you look at what they actually did, if you take this signal and you ask how much does the foreground changes in order to get to this very small RMS, you see that the change in the foreground is of order the size of the signal. So they changed the foreground in an opposite way in order to absorb the signal that they were looking for, which makes no sense. Okay, and they did it, and you could do it in several ways. And in fact, you see that if you just take this sign and add it to the foreground, then you get similar RMS, even though now your foreground plus this background, whatever it is not large. So that tells you that that's what you really need to do. It tells you that we don't really know what the background and foreground of this experiment is, but what we're seeing is probably that and not a signal that somehow miraculously kind of cancels out with the foreground that we find. So that's the bottom line. And so what you can do is just focus on that, and instead of thinking of a signal, just ask now you have a constraint. Now you just have this noise, and you ask what kind of new physics models would supersede this noise, and so we can constrain them. That's the idea. And there are other measurements, not just edges. Saras 3 came out last year, and okay, you see it here, different frequencies, different redshifts. Before Saras 3, there was Saras 2 that has results on much larger frequencies that unfortunately I'll mention you cannot use. And there are others. Bottom line, this is this blue here is the edges signal when you subtract this, use the sign, and you see these other modes. You don't see Saras 3, which would be somewhere here. But now you have several measurements, use them to constrain new physics, okay? So it's much harder because constraining things you can't. I mean, if you want to have a believable answer, you can't just bullshit and assume take the best case scenario, which is what I showed you here, and you have to take into account astrophysical uncertainties, and there are many. And the main two astrophysical uncertainties are X-rays and Lyman-a radiation, and we have to take them into account, and that's what I'm going to explain next, how we do that. Okay, so let me just spend the next half hour on that, and then we'll move on. So Lyman alpha, and the point of Lyman alpha, once stars are formed, you have radiation, and that radiation can cool the gas through this Woods-Tausend field effect, and I'll tell you how that happens, and then we'll talk about radiation, which X-ray radiation, which heats up the gas eventually, and shuts down this whole absorption signal. Okay, so the idea behind the Woods-Tausend field effect is the following: because Raman scattering, Lyman alpha radiation comes in, excites the hydrogen to some excited state, and when it comes back, it spin flips. So there's a spin flip interaction. But the point is that there's a Doppler shift because of the thermal temperature of the hydrogen, and this means that in every such interaction, you actually influence the temperature of the hydrogen, and so that's what drives the spin temperature down to the baryon temperature, simply because this becomes very fast, and once this is fast, then it influences also the temperature of the gas, and it couples the two back together. So that's the Woods-Tausend field effect in I don't know, 20 words. But really, and it could be, of course, if the baryon, you get an absorption signal if the baryons are colder, and you get an emission signal if the baryons are hotter. And the way to calculate it is you need to calculate, you remember this was the solution to the Boltzmann equation to extract the spin temperature. And for that, you need to kind of figure out what is this rate. And this rate of Lyman alpha is proportional to the absorption cross-section at the line, Lyman alpha line, times the flux of photons around that frequency. Okay? Now, the point is that we need to calculate, we need to write down some equation that describes this photon flux. And what people usually do is they do it very simply. They say, well, then if I plug it back in and I take just suppose I have a constant flux of photons around the absorption line, that this is just some, so there is some constant flux, yeah, and so X alpha will be some number, okay, times the efficiency, and the efficiency is essentially taking into account the fact that there is no constant photon line, but there's actually an absorption line around the Lyman alpha photon, and that's what I want to show you. So there's some efficiency which describes how much is the, if this is 1, then Lyman alpha is extremely efficient, and all these photons around the absorption line just get absorbed and get re-emitted and couple the two back. But the point is that in order to find this, we need to write down some Boltzmann equation that describes the flux around the absorption line. And it's quite hard. I'm not going to go into the details. You could expand this Boltzmann equation to get to a Fokker-Planck-like equation where you get diffusion coefficient, which essentially comes from the fact that there's some thermal broadening of this line. So you could go up here and then come down from here. So it's like changing the flux that is being re-emitted. And you have a frequency shift just because when the photon comes in and gets reabsorbed, there's a kick to the nucleus, which again shifts its energy. So so both of these depend on the temperature of the gas in different ways. And so once you take this into account, you can see that the flux, okay? So look at the top one. Let me not mention the bottom one right now because we don't have time, but look at the top one. This is the photons that redshift into the Lyman alpha regime. And at high temperature, what happens is that, if there's high temperature, these photons, these absorbed and re-emitted photons can go back into even higher temperature than the Lyman alpha. So they spread, this whole line spreads. Whereas at low temperature, there is simply an absorption signal around the Lyman alpha regime because all these photons get absorbed. So at low temperature, there are not many Lyman alpha photons that can couple the two, the spin temperature and gas temperature together, the two baths together. Okay, so low temperature, the efficiency of Lyman alpha drops simply because there aren't that many photons around the Lyman alpha frequency. Okay, not sure I was clear enough here. So ask if you have questions. But the bottom line is that if you draw the frequency, the efficiency, then you see that it drops with temperature. Okay, so that just tells you that if you cool too much the baryons, then the temperature drops, efficiency drops, and then the spin cannot couple to the baryons, simply because the efficiency of Lyman alpha, of the Woodhouse field effect is dropping. And what that produces for you is some signal, another dip in the spectrum, that because you start cooling the baryons, for a while the spin temperature can follow the baryonic temperature until the baryons are just too cold and Woodhouse field effect shuts down for a while until Lyman alpha spectrum is the flux is so loud that it doesn't matter what the coupling is. There are so many photons that eventually it recouples again, and that's why you see two dips here and not just one. Okay, so there's a signal you can actually look for. There are all kinds of caveats. This whole thing has been calculated and verified only up to 1 Kelvin, and when you cool with dark matter, it goes much below the 1 Kelvin, and so on. So I'm gonna skip all of that. Reionization, you could only probe what the tools that we are using can only work until reionization becomes important, simply because we are taking the sky average and not the fluctuations. So I'm not going to go into that. And let's just quickly move and discuss X-rays for a second. So Lyman alpha, again, were relevant for coupling the spin to the baryons, but then X-rays come in and heat up the gas and generate and kind of close the peak, the absorption peak at low redshifts. So how do you take that into account? You need to add X-rays to this Boltzmann equation that I wrote before. And this depends strongly on the X-ray flux. And the X-ray flux is a unknown quantity that strongly depends on the rate of star formation. So there's some star formation rate. We form stars early on, and we need to know what this rate is in order to extract how many photons we expect from X-rays. Okay, because if you want the main production, one of the main production mechanisms for X-rays is just black holes or mini quasars where stars just get eaten up and produce X-rays in the process. So that's the source. So we need to know how many stars you're producing, and how many stars you're producing depends on the so the halo mass function. So how many halos you have in a given mass, and how many stars you expect to be formed for a given mass, a given halo. Okay, so this is the star formation efficiency. And so everything is model dependent. The only thing we know comes from measurements. These are Hubble measurements at late time. So we only see stars that were formed rather late. Okay, these are so-called POP2 stars, and so we can only be sensitive to the efficiency, star formation. This is the star formation efficiency density, but you're sensitive to the star formation efficiency at late time, where you're dominated by massive halos, very massive halos. Okay, so we only know this regime. We cannot see POP3 stars, and so this is the regime with massive halos. All these models agree, but there are many models in the literature that discuss how stars what is the star formation efficiency as a function of the halo mass. Okay, and again, I'm not going into the details here just because Chaba, I think, is really serious about my 45 minutes. Anyways, yeah, we'll only talk. Diego said yesterday that we'll only talk about 21 centimeters. Yeah, I think it's true. Anyways, so that's what I want, the take-home message here, without me giving you many of the details, is that there's huge uncertainty on what star formation efficiency looks like, and therefore huge uncertainty on the X-ray flux, and therefore huge uncertainty on the brightness temperature or the spin temperature. And if you pick up one of these astrophysical papers, that's what you'd see, right? So this is Z going in this direction. So early time is here. This is the brightness temperature, T20, what I called T21 before. So you couple to the baryon, to the CMB at early times. Okay, then there's a dip. Okay, and you see what happens as you change the amount and you heat up. This heating up is due to the X-rays. Okay, and if you change the star formation efficiency, this changes, but also this, because if you are very efficient at producing stars, then you start producing X-rays early on, and then you heat up the gas very early on. So there's huge uncertainty, and people have been studying with 21 centimeters, have been studying all the constraints of these kind of models. This is why I'm saying the realization and the early times, these kind of time regimes are very useful. You can study those with 21 centimeters. That's what the astrophysicists are doing. And
can I make a positive comment about
sure.
That I never noticed now that it's so big? If you follow every single line, notice that there is always a dip. Okay, and that's because like between Lyman alpha fluxes and X-rays, there is always a delay.
Yeah, but where the dip is strongly depends on the model, and therefore what type of measurement you need in order to constrain it strongly depends on the model. I will, as I said before, that what we can do right now is only study until realization. So models that measure this spectrum, we just can't. So 10 and below, we just can't do. Okay, so for instance, SARAS-2, which measures this regime, we just can't do right now, because for that you really need to take into account fluctuations. You can't do sky average. Because reionization strongly depends on the evolution near the stars in regimes where you actually ionize all of the gas before more light escapes and reaches the intermediate, the intergalactic medium. Okay, this is just to say that if you take X-rays into account, you see a lot changes in your predictions for the 21 centimeters. And now you can see, I showed you a simple evolution at the beginning, but now you can see what it actually looks like when you take into account all these details of Lyman-a and X-rays. And these are the baryons, and you see, you start following the baryons for a while, you generate a small peak, then Lyman alpha really takes over, and you couple the baryons, but not all the way because of the finite efficiency, like Woodhouse fields efficiency, and then X-rays takes over, and you heat up with that. So that's what it actually looks like. And we are studying all these uncertainties in order to understand what can you actually say. And these are the current answers. Okay, these are not constraints yet. These are in our first paper that we are writing right now. We are not placing yet the constraints, but we are just showing what the signal would look like. So if we zoom in here, okay, you see this is what we expect to have for the temperature at the minimum of the absorption peak. Okay, and we can probably probe for this, and this is the two fluid case, and we can probably probe this regime. This regime stays open, unfortunately, with the two fluid for the two fluid case. So yeah, that's unfortunate, but it is what it is, and it's because in the two fluid case we are not very efficient at cooling the baryons. By the way, the constraint will be better than this line, and the reason is that correlated features would be because when I show the data, all these data points are correlated. They come from subtracting some foreground, and so you get correlated noise. And if you take this into account, you are more sensitive to features, which means that we'll probably probe some region here, but not all of it. We will know very soon. If you look at the free fluid, it's much more optimistic, and we will probably be able to constrain most of this regime. We can probably close most of this regime with data that exists already. Okay, so again, we will have a result very soon, but there is very little region that we expect to have for satellites that I mentioned. Still open regime, but not as big as it was until this will come out. All right. So that would be on my next thing. I can just advertise it. I will not explain anything, but I'll just say the idea is that, of course, dark matter can forget about this. Of course, dark matter can have dark sectors can have structure, and therefore self-interaction, dissipation, and so on. It can fall into stars, or it can be asymmetric dark matter, which falls into stars. And then you could ask a really stupid question, which is what we were asking: how much are we sure that there's no dark matter inside stars? What is the constraint on dark matter inside stars? And the way to attack it is look at what is called double-line spectroscopic binaries. Those are binaries where you see the spectrum of both stars. So, and you see the eclipse. And if you see the eclipse and you know the radial velocities of both stars, you can extract their masses, just Kepler's law. And so you have the gravitational mass of both stars. Now, you need to ask, if there was dark matter, it would change the gravitational mass, but not the luminosity of those stars, and therefore, well, it would also change the luminosity, but in a different way. And so you can disentangle the two and place constraints on the amount of dark matter, because you throw dark matter into those stars, you change the gravitational, but the luminosity changes in a different way, just the equation of state for those stars. So that's what we did. We wrote the equation of state and we solved it. And bottom line, and I'm jumping ahead, there's a big catalog of these SB2s, and the bottom line is that you have these constraints, and roughly speaking, the the main constraint is that you can't have more than 5% of dark matter inside stars, and you can probably improve this limit by a lot with more data, and there should be more data.
Which are the stars that set the strongest constraint?
Sorry?
Which type of stars set the strongest?
Right, so all these stars are main sequence stars, and you divide them into different masses just because of the energy production mechanism, whether they are. So also you could show that all of these stars by and large are dominated by gas pressure, and so but depending on the metallicity and various other and the masses of these stars, they behave. I mean, their energy production is slightly different, but they all be. You see that the fit is perfect, right? That's what also astrophysicists do. The light to mass ratio is always given by some mass to some power. It's this type of thing, and Q here is the amount of dark matter. Okay, so the total mass over the dark matter mass. Yeah. So bottom line is that you always have some light to mass ratio like that, and you can fit and you can fit it. It fits very, very well, and all of these are main sequence stars. And in fact, it already tells you that you don't. The fact that it fits so well to this thing, it already tells you that you can't have too much dark matter inside. And the reason is that otherwise they would radiate. You know, if you throw in dark matter, they are much more luminous. And the reason is that there's more gravity that pulls. To stabilize them, you need some radiation pressure, and that gives you a lot of radiation. So they would move out of the main sequence if there was a lot of dark matter inside them. So yeah, so these are cool constraints, and you can constrain asymmetric dark matter and a double disk and dissipative dark matter, which we haven't done it. So these are things we're planning to do, relatively long-hanging fruits. This is not, but this is. Anyways, all right. Yeah, and there's no skip. You see, I really plan to skip here, but there's no. It's a PDF now. So I'll just give you another. I'll just continue. No, I'm joking. I'll jump. I'll ignore these very cool stuff, but ignore it. And yeah, and these are the conclusions. The main conclusion is have fun while you're looking for dark matter. But yeah, there are lots of opportunities with astrophysics and cosmological data, as we all know. And I gave you one example, 1.5 example. Thanks. Thank you.
You're faster than Mitchell.
Sorry?
You're faster than Mitchell.
Yeah, you see? I can continue if you just let me.
Okay. Yes.
How well are known the equation of this?
No. So okay. So everything. So what we've done, which is completely sufficient, is to not solve it entirely, but you could use. If you look at these. If you look at these equations, and now you just vary them to ask what happens if you have additional dark matter. So you see, not much is varied. And to solve these equations, of course, is very difficult, and people are doing them with simulations. But you don't need to do that because we fit into data. And what astrophysicists do very often is just to use so-called something which is called a homologous. I don't know how to say it. It's a similar kind of stellar model, and then these equations just turn into algebraic equations where all you care about, you see, you can solve what happens in a gas in a radiative diffusion with gas pressure or radiative diffusion with radiation pressure, and you get all of these always behave like a parallel. So you don't, and we're not assuming any one of those, we're just fitting to the data. Yeah, taking into account the astrophysical variability, so it's not just statistical variability. It's clearly that metallicity changes a lot and many other factors change. So we take that into a statistical account, and so we just fit to the data. And that's exactly when astrophysicists tell you what is the light to mass ratio, they do exactly that. There are models that they are building intricate models and simulations in order to look at specific stars and try to understand them. But it's not important when you actually want to look at data. And you see, the fits are fantastic, yeah, for each. So this is not, we took the same division as what these papers did, And you see, for each mass regime, the fit is fantastic with a small scatter, and that's what drives such a strong bound.
Have you thought about like what kind of models actually could even accrete to?
Yeah, so asymmetric dark matter can accrete.
Asymmetric can,
Right.
but can anything else?
So a double disk would accrete.
Okay.
And then dissipative dark matter, which is the hard part, which I said that is why it's not a low hanging fruit. Sorry, but it's something very interesting. Is dissipative dark matter would create small objects, and then you need to ask, how much. So you expect some of the dark matter to fall into the same potential wells as the baryons, and so we do know that they follow each other. And so now the question is dynamical question of how much do you expect those dissipative dark matter to fall into baryonic stars? And it's an interesting question which I don't know the answer to, and I think it's difficult because it relies on intricate dynamics. But it's a game that one should do.
Are you imagining this happen like when the star is forming, or is there some capture?
It's very I mean, clearly the cooling mechanisms can be slightly different. Yeah, I mean the coupling is different, and therefore the time scale could be different. But the filaments and the potential wells are the same. So then you need to ask what's the probability. It's a question which you could do to some extent, and it's an interesting one which I haven't done. Yeah.
Any more questions?
Yeah, I have one. So how much this? So here are you assuming the sphericity of?
Yeah.
Spherical symmetry.
Yeah. Yeah.
Because I would expect like this is not realistic, no?
Why not? Stars?
I mean, if I have dissipative dark matter,
This is inside the star. These are falling to the center of the star. This is not a galaxy or anything like that.
No, but even
this is accretion. They fall gravitationally. What I'm assuming here is that there's no dark radiation, or there's this dark star from.
No, but let's say if like even like within so if you would redo the fit, but just like allowing for just
elliptical
shapes.
So first, we don't have data like that, so I don't know what.
Now, what do you mean? Right, the data you have, you can just modify.
No, data about the shape of the stars. I'm not aware. You don't see that usually. The shape. If you want to use,
you don't have information, but you don't. Since you don't know, you could just ask yourself how much it depends on the.
Yeah, so I very much doubt that it changes the general. So first of all, you see, to begin with, we're looking at very small amount of dark matter to begin with, because otherwise it's inconsistent. As I said, the main constraint would come that you would drive you away from the main sequence. So
no, let me.
To begin with, there can't be a lot of dark matter.
Now, this is what I'm worried about. Okay, so what you're using here, I think, is just that if dark matter goes in, as you said, like there is a lot of gravity, then like everything is pulled, and then you get more radiation.
Yes.
Now, if I break this, so that then instead of like, instead of that I can throw some of this energy into the formation of the geometry of the system.
Well, I remind you that baryons do that. They're still spherical. There is no reason for it not to be spherical.
The reason is the presence of dark matter.
No, but the dark matter.
You don't know the dynamics. You're not solving for
No, sure, but you need to somehow, for a reason which I don't yet understand what you have in mind, you need the dark matter not to be spherical inside. And if these are two fluids that behave the same and just feel the same gravity, what drives them away from spherical symmetry? The same way as stars. Stars are spherical.
Can have its own dynamics. And
if the angular momentum is large, then I'd agree with you. But in any star which the angular momentum is not large, that's sphericity.
But you know the angular momentum of the stars that they're using.
First, I don't think I do.
Yeah, so you see.
No, it's the same. You want to assume that somehow the 5% dark matter there changes whatever is inside the regular behavior of the star by a lot. For stars, which you can also have forget about dark matter. Stars, which can also have angular momentum, then of course, there's some deviation from sphericity. The deviation is small and it would not change the LMR, the light to mass ratio. Same thing happens here. If something else happens, then there must be completely different physics which you have in mind. I don't see it happening. Again, remember we're talking about 10% dark matter. Yeah? That's our starting point. Otherwise, we already know that that's immediately excluded by the main sequence argument. I don't see this happening. Maybe I'm wrong. I'm happy.
All right.
All right, thanks.
Let's thank Homer again.